The Earth's geological changes following the end of human activity herald a new chapter in the planet's history. Natural processes take over as human impact declines, reshaping ecosystems, changing landscapes, and leaving their marks on geological records. This article explores the different facets of the transition, such as landforms, erosion, sedimentation, climatic impacts, and the legacy of human impact on the geological timeframe, as it explores the geological changes that are occurring on Earth after the extinction of humans. Unveiling Earth's power amid geological transformation. The resilience of nature. The resilience of nature is revealed by the Earth's geological alteration following the cessation of human activity. Natural processes take center stage when human interference is absent. They rehabilitate ecosystems, shape landscapes, and adjust to shifting environmental conditions. This section highlights ecosystems' ability to recover, adapt, and flourish in a post-human period by examining nature's amazing resilience amid geological transition. Ecosystem comeback. Ecosystem regeneration is one of nature's most remarkable displays of resilience. When ecosystems are not subjected to human-induced stressors, they can recover and resume their natural ecological roles. Wetlands recover their normal hydrological cycles, forests regrow, and grasslands thrive once again. Ecosystems are resilient because of their innate capacity for self-healing and adaptation, which allows native species to repopulate and re-establish complex ecological connections. Adaptation and succession. Ecosystems experience succession as a result of geological transformation, which is a process that gradually modifies the species' composition and structure throughout time. Grass and shrub species are pioneer species that settle in disturbed environments and set the stage for the emergence of more complex ecosystems. Nature exhibits its flexibility through ecological succession, whereby early colonizers are replaced by species that have specialized features and are resilient to certain environmental circumstances. Ecosystems that are stable and diversified are developed as a result of this succession. Evolution and genetic diversity. Genetic variety plays an important role in nature's adaptability. For an organism to survive over the long term and be resilient to changing environmental conditions, it must be able to adapt and develop. Within a species, genetic variety facilitates the development of individuals with favorable features that help them deal with novel situations. Natural selection gradually affects these differences, giving preference to those who are more suited to the post-human environment. The resilience and sustainability of ecosystems are guaranteed by this continuous evolutionary process. Adaptability to unrest. Nature has developed defense systems to tolerate and bounce back from a variety of shocks. Volcanic eruptions, floods, and wildfires are among the natural disruptions brought about by geological upheaval. Ecosystems have developed coping mechanisms in response to these occurrences. To recolonize following disruptions, many plant species, for instance, have evolved fire-resistant characteristics, while others depend on seed banks or quick growth. Ecosystems are incredibly resilient, even after traumatic occurrences. They recover and resume normalcy. Coexistence and mutually beneficial arrangements. The cohabitation and symbiotic interactions between species serve as more examples of nature's tenacity. To be balanced and functional, ecosystems depend on intricate webs of interactions, including seed distribution, predator-prey dynamics, and pollination. These connections can resume flourishing in the absence of human interruption. Pollinators and blooming plants, for example, re-establish mutualistic interactions that guarantee the survival of both parties. The interaction and connectivity of species within ecosystems is what gives nature her resilience. Climate's adaptive capability. A key factor in nature's ability to adapt to geological change is its climate. Climate patterns impact ecological processes, dictate habitat appropriateness, and affect species distribution. Ecosystems can and have adapted to shifting climatic conditions over the course of Earth's history. To adapt to shifting climates, species may change their phenology, expand or contract in range, or evolve new adaptations. The ability to adapt guarantees that ecosystems will remain resilient despite continuous changes in climate. Evolution of landforms during geological transitions. When there is no human activity, geological change results in the evolution of landforms, which reshape the Earth's surface over extremely long durations. The Earth is shaped by natural processes that include weathering, tectonic activity, erosion, and sedimentation, which take center stage in shaping landscapes. In order to demonstrate the transformational strength of Earth's geological processes, this section examines the dynamic process of landform change under geological transformation. Weathering and erosion. Fundamental processes that sculpt landforms throughout time are weathering and erosion. These natural, unassisted processes are made possible by geological alteration. Valleys, canyons, and coastal features are progressively carved by the erosion of rocks and the movement of material caused by rivers, wind, glaciers, and waves. Landforms change and adapt to their surroundings, demonstrating the power of wind, water, and ice to modify landscapes. Stream-bed landforms. Water-driven fluvial processes are important for the development of landforms. Rivers sculpt the surface of the earth by eroding and moving debris downstream, creating valleys and channels. Rivers alter their paths when geological alteration takes place, creating floodplains, meanders, and braided channels. Rivers sculpt the terrain throughout time, widening valleys and establishing complex drainage networks. Landforms and glaciation. The evolution of landforms is significantly impacted by glacial activity. Glaciers can advance and recede in areas where they have occurred or now present due to geological alteration. U-shaped valleys, jagged mountain summits, and cirques are all created by glacial erosion. Moraines, glacial lakes, and glacial outwash plains are remnants of the glacial retreat. The terrain is shaped over thousands of years by the glacier's gradual flow, leaving behind distinctive landforms that serve as reminders of the planet's glacial past. Landforms along the coast. Geological processes cause substantial alterations to coastal habitats. Coastlines are shaped by wave action, tides, and currents, which also deposit sediments and erode cliffs to create a variety of coastal landforms. Beaches, dunes, barrier islands, and estuaries are the natural responses of coasts to variations in sea level brought about by geological modification. Coastal landforms represent the dynamic interaction between land and water and act as markers of historical and contemporary fluctuations in sea level. Tectonic features. An important factor in the development of landforms is tectonic activity. Mountains, rift valleys, and fault lines are the products of the natural movement of tectonic plates made possible by geological alteration. Mountains grow and crumble as tectonic forces press against the Earth's crust, sculpting huge landscapes. Tectonic landforms are dynamic due to the action of earthquakes, volcanic eruptions, and the creation of new landmasses. Landscapes with karst features. Karst landscapes are constantly changing as a result of geological transition. They are created when soluble rocks like dolomite, gypsum, and limestone dissolve. As water seeps through the joints and fissures in the rocks, it progressively dissolves the minerals, forming distinctive structures like sinkholes, caverns, and subterranean drainage networks. The way karst landscapes change demonstrates how hydrological dynamics and chemical reactions influence landforms. Influence craters. Impact craters left behind by meteorite strikes on Earth's surface may be preserved and identified thanks to geological alteration. These craters are evidence of the transforming potential of alien impacts since they were created by strong, apocalyptic events. The history of the Earth and the influence of cosmic forces on the planet's formation are both greatly illuminated by impact craters. Impact of humans on landforms. Although geological alteration highlights the transformational force of nature, human impact on landforms must also be acknowledged. The surface of the Earth bears the scars of anthropogenic activity like mining, deforestation, and urbanization, which have changed the terrain. These alterations to landforms brought about by humans coexist with natural processes, acting as a reminder of the connection between geological changes and human activity. Climate, revealing Earth's autonomous systems amidst geological shifts. The Earth's climate system is greatly influenced by the climate. Natural processes take back control throughout the geological transition process, affecting climatic patterns and controlling Earth's temperature. This section examines the complex system of climate that is driven by geological transition, emphasizing how Earth adapts to changing climatic circumstances through self-regulating systems. Carbon. Carbon is essential to comprehending the dynamics of the climate. Carbon cycle can be regulated by natural processes thanks to geological change. Carbon dioxide, CO2, is absorbed by photosynthesis when ecosystems recover and vegetation grows again, lowering atmospheric concentrations. This negative contributes to the stabilization of world temperatures by reducing greenhouse gas emissions. Comparably, decomposition and oceanic circulation are two processes that can liberate carbon trapped in terrestrial and marine systems, leading to positive feedback that intensifies climate change. It is essential to comprehend the equilibrium between carbon intake and release in order to forecast future climatic scenarios. Albedo. The reflection of the Earth's surface is referred to as albedo. Albedo can be influenced by natural processes due to geological alteration. For instance, the albedo drops as ice caps and glaciers melt and reveal darker surfaces like the ocean and land. A positive feedback loop is created when reflectivity decreases, increasing the amount of solar energy absorbed and causing more heat. However, the recovery of flora and the establishment of forests can raise the planet's albedo, which will reflect more sunlight and cause it to cool. The impacts of global warming are amplified or attenuated by the interaction between increasing surface reflectance and climate. Water vapor. One potent greenhouse gas that may either exacerbate or mitigate climate change is water vapor. Changes in precipitation patterns, evaporation rates, and the area of water bodies are some of the ways that geological transition affects water vapor. A positive feedback loop is created as the temperature rises and more water vapor is taken up by the atmosphere, intensifying the greenhouse effect. On the other hand, more precipitation and cloud cover can have a cooling effect and more reflecting surfaces. Forecasting future climate trends requires an understanding of the intricate relationships that exist between temperature, atmospheric conditions, and water vapor. Cloud. Clouds influence the climate in two ways. They are able to both exacerbate and lessen climate change. Natural cloud production is possible again because of geological alteration. Low-lying clouds, like stratocumulus clouds, chill the environment by reflecting sunlight. But high-altitude clouds, like cirrus clouds, trap heat emitted by the Earth's surface, causing global warming. Cloud cover, composition, altitude, and other elements all affect the overall impact of clouds. Predicting future climatic situations requires accurate cloud modeling and comprehension. Flora. The climate is significantly influenced by vegetation. Vegetation enters the picture when ecosystems emerge from geological upheaval and recover. Elevated levels of plant cover result in elevated rates of evapotranspiration, hence impacting both local and regional climate trends. The temperature, humidity, and formation of clouds can all be impacted by the release of moisture from plants into the sky. Furthermore, vegetation affects the carbon cycle by reducing greenhouse gas emissions and sequestering carbon through photosynthesis. The significance of protecting and rebuilding natural ecosystems is underscored by the complex interaction between vegetation and climate. Ice albedo. One important aspect of the dynamics of the climate is the ice sea level. Ice albedo processes that occur naturally are made possible by geological alteration. The exposed darker surfaces of melting ice caps and glaciers absorb more sunlight, causing additional warming and ice melt. This feedback loop intensifies the effects of climate change. On the other hand, when ice caps and glaciers expand, the Earth's reflectivity rises, decreasing solar radiation absorption and causing cooling. Comprehending the function of ice albedo is essential to understanding the stability of polar areas and patterns of global climate. Oceanic. The climate is significantly influenced by the oceans. Natural oceanic processes can be restored through geological alteration. Heat distribution, nitrogen cycling, and carbon absorption are influenced by ocean currents and thermohaline circulation. Both regional and global climate patterns may be impacted by modifications to oceanic circulation patterns. The ocean also absorbs CO2 from the atmosphere, functioning as a carbon sink. However, excessive carbon absorption can cause ocean acidification and disturb marine organisms. The complex link between the oceans and Earth's climate system is highlighted by the interactions between oceanic and climatic factors. The Earth's self-regulating capabilities in reaction to changing environmental conditions are demonstrated by the climate under geological transition. The intricate interactions that make up Earth's climate system include those caused by carbon, albedo, water vapor, clouds, vegetation, ice albedo, and oceanic conditions. Comprehending and precisely simulating these systems is vital in forecasting forthcoming climatic situations and formulating efficacious mitigation tactics. Understanding how strong Earth's self-regulating systems are emphasizes how crucial it is to protect and restore natural processes in order to provide future generations with a stable and sustainable climate. That's all in this video. If you like the information, please hit like and subscribe to this channel, and be connected to this channel for more space information.